what can you have? Just like this. Data trace, the blue curve. After Fourier transform, you have something like this. DC term, you have a very sharp delta function. And at omega 0 and minus omega 0, you have some frequency components. And they are roughly symmetric. Okay. And spatially, this function is a real function. After transform, this is a real function. So I can plot the function with a single curve. I do not need two curves. But why is the function real? According to the Fourier transform property, if this function is even function, after transform, it is a real function. Is it okay? 其实很简单嘛，你如果这个函数是偶函数，那你做 transform 是要乘上那个 kernel 叫 exponential minus j omega t， 对不对？它有 cosine 是 real part，sin 是 imaginary part，sin 是奇函数，所以 sin 跟它相乘，就偶函数乘奇函数会变成奇函数，那你全部积分起来就是0，所以 imaginary part must be 0。It is a real function. That's it. Then step 2, extract the component centered at carrier frequency omega 0, which is here. Okay. So there are 3 components, but I'm only interested in this one, centered at omega 0. So roughly speaking, it's G1 tilde of kappa minus omega 0, according to the previous page. Right? Mathematically, there are 3 terms, term 1, term 2, term 3. And I only need this one, so this is the second term, G1 tilde of kappa minus omega 0. Step 3, shift this part to the baseband, meaning kappa around the 0 to get G1 of kappa. Okay, so just like this illustration. After extracting the second term, I shift the entire term to be around kappa equals 0. So I use a shaded area to highlight what happens after the shift. Okay, and the mathematically it's G1 tilde of kappa. Finally, just performing inverse Fourier transform. Okay, after you got G1 tilde kappa, you just perform inverse transform. You can get G1 of tau, and this time G1 is a complex function, so I need the blue and the red curves to illustrate the magnitude and the phase of the complex function. And that's it. Within 4 steps, you can recover the complex function G1 by initially a purely real data trace. Any question? 所以实数的 data 里面其实隐藏了复数的一个函数，那你可以用这个固定的4步的方法把复数函数找出来啊，不止 magnitude 找得出来啊，连 phase 都可以找出来。And the only tool you need is Fourier transform. So it's a very useful tool in signal processing. Okay, any question? Okay, however, there are some problems about field autocorrelation. The first is lack of spectral phase. Field autocorrelation function is nothing but power spectrum. It is the conclusion, but we need to prove it. So here I show you the mathematical proof. Sorry. Let's check G1 tilde. Because we know Fourier transform does not change the information. It just represents the same function in 2 different domains. So if you want to know what is the information implied by G1 of tau, you can just analyze the information contained by G1 tilde. They are the same. Okay， 所以你看看 frequency domain 的函数，它告诉你是 by definition is Fourier transform of G1 of tau. So by definition is proportional to a double integral, right? First, G1 function is already an integral here, the inner part, integration of a of t times a of t minus tau complex conjugate, integration with respect to variable t. So this part means G1 according to the definition. And for the purpose of Fourier transform, you have to multiply the kernel function e to the minus j kappa tau and the integration over the second variable tau. So it's a double integral representation. Right? Now, we change the variable kappa to variable omega because we are more familiar with omega. 所以只是把符号有 kappa 的地方就是在这里换成 omega. That's it. So what do you have? Now, G1 tilde of omega is proportional to a still double integral, but replace kappa by omega. But this is a double integral, so you can switch the order. Okay? Initially, you integrate with respect to t first, then with respect to tau later. But you can switch the order. Integration with respect to tau first, then with respect to t later. And for that reason, you can extract everything irrelevant to variable tau outside of the first integration. Okay? So a of t is nothing to do with variable tau, so it's outside the integration. A star of t minus tau is here. E to the minus j omega tau is here. So it's in the inner integration. Okay. Now we change the variable again, assuming a new variable t prime as t minus tau. Okay. So what happens? T minus tau becomes t prime. Tau becomes t minus t prime. Okay. D tau actually becomes minus dt prime, but the minus sign doesn't matter because we have a proportional symbol here. Okay. So that's it. Then you can rearrange the integration again. You see t prime is here, t prime is here, dt prime is here, so they can extract together. T together, combine them together. So you have multiplication of two one-dimensional integrals. The first one is about t prime, the second about t. But interestingly, you see complex conjugate here, and for variable t prime, you have actually e to the positive j omega t prime, which is different from the standard kernel function of Fourier transform. Standard kernel, you need a minus sign, but it doesn't matter. Just give it a minus sign, but add the complex conjugate outside the integral. Okay. So actually, the two one-dimensional integrals are essentially the same. Just replace t prime by t. They are exactly the same. The complex conjugate is the only difference. Okay. Now, what is the individual integration? This is by definition, it's the Fourier transform of small a of t. But according to our notation, what is the Fourier transform of small a of t? Big A of omega, right? So from temporal envelope function to spectral envelope function, right? So that's the answer. This is A star. The second integral is A. You have A star times A, which is absolute square of A. But what is the meaning of A absolute square? The power spectrum, right? So what I have done is all the effort you spend to measure the field autocorrelation, it turns out that it is equivalent to measuring absolute square of A, which is the power spectrum. If that is the truth, it means there is no spectral phase information at all. 你完全没有得到 spectral phase information. 你得到的只是 power spectrum. But we have mentioned it is much easier to get power spectrum. You just need a spectrometer, right? So it means you build a microsensor interferometer to perform self-optical gating, but it turns out that it's equivalent to building a spectrometer. 所以第一时间你会觉得哇，这个浪费力气啊，没有得到任何新东西。但实际上它还是有它的用处啊。It is useful in making spectrometers, the interferometric type spectrometer. 所以实际上这个光谱仪也有两大类啊，一类是绕射式 ，maybe 有 grating 啊，加 detector array 可以取得光谱。另外一个就是这个东西，干涉式的光谱，架一个麦克森干涉，那你只需要一个 point detector， 你可以得到 field autocorrelation trace after signal processing. You've got the power spectrum. Okay, you've got the same information. And sometimes the interference type in the spectrometer is more popular at a certain frequency range, especially mid-infrared range. 中红外光的波段里面呢 ，grating detector array 都会变成问题 ，especially detector array is extremely expensive to have a mid-infrared detector. Not to mention array. 一颗就很贵了，要买一个阵列，贵得不得了。But if you use microsensor interferometer, you just need a single point detector. You do not need an array, right? And you can still get the power spectrum. And usually it's referred to Fourier transform infrared spectrometer or FTIR spectrometer. Okay, it's a very useful tool in material science. Okay, any question? So here is a pretty striking information. Okay, since field autocorrelation does not give you any spectral phase information, it means it cannot distinguish 3 different types of pulses. Type 1 is a short transform limited pulse with constant spectral phase. Type 2 is long chirped pulse with maybe a quadratic spectral phase. Type 3 is incoherent noise with random spectral phase. Okay, so I show you 3 examples here. The shaded area is the transform limited pulse with constant spectral phase. The red dashed curve is the chirped pulse with quadratic spectral phase. The blue curve noise-like waveform is an incoherent noise with random spectral phase, but they share the same power spectrum. As long as they have the same power spectrum, they must have the same field autocorrelation trace. Okay, so you see how limited information can we obtain by FA measurement. 你连这3种都分不出来，就得到同样的 field autocorrelation trace. So that's certainly a problem. Bonus question. Why a long chirped pulse still gives rise to a narrow field autocorrelation trace? So let me clarify this question a little bit. Okay. See, the transform limited pulse is a narrow pulse, right? So as we mentioned, when the delay is larger than the pulse duration, the overlap is small, right? So the product is small, so you have a small autocorrelation value. So you can expect the field autocorrelation trace, the correlation width could be related to the width of transform limited pulse in the same order. But the second case, chirp pulse, in time domain is pretty broad because of the chirp. So it means when these two red pulses separated to several times of the transform limited pulse width, they are still partially overlapped, right? If they are still partially overlapped, we expect their product is not zero. The autocorrelation values should be still large, right? But the theory tells us the red broad chirped pulse still gives the same autocorrelation trace as transform limited narrow pulse. So it means even though the two chirped pulses are still partially overlapped, the autocorrelation value drops a lot, maybe down to 0. Why is that?知道我的问题吗？我们只看前两个例子，转换极限的窄脉冲跟带有 chirp 的宽脉冲，数学定理告诉我，它的 trace 是一模一样的。好，那对转换极限脉冲来讲，它很窄，所以这一个 trace 的宽度叫 correlation width， 大概就是转换极限脉冲的宽度类似。所以它应该也是窄。那但是这个红色的 chirp pulse 它很宽啊，可是它却会得到一个窄的 autocorrelation trace， 也就代表当你在 scan 这个 delay 的时候，即使红色的脉冲因为它宽，它 overlap 的情况还很明显的时候，它的 autocorrelation value 已经掉下去，它才会得到一个窄的 autocorrelation trace， 对不对？可这不是很奇怪吗？你还有 partial overlap, but your autocorrelation value is near 0. How could that happen? Bonus question, yes.
因为就是 G1 它可能是一个 complex function， 那可是呢，你在算field autocorrelation 的 intensity 的时候，你只有取它的 real part， 所以可能有其他不一样的地方隐藏在 measurement part。
Okay, you hit the central point. Yes. Let's check the definition of field autocorrelation function. Here. Okay, so this is the definition. Just look at the numerator. Forget about denominator. It's nothing about the shape of the trace. Complex function A times complex function A of t minus tau complex conjugate. So of course, envelope matters, but phase also matters. 这是两个复数函数乘积的重叠积分。所以即使你只看绝对值，它还重叠得很好，那么它的乘积就不应该接近0嘛。我应该预期了一个很大的 correlation value。But in reality, if they have very different phase, A 跟 A of t 减 tau 就不同的时间点，它的 phase 如果差很多，那你把它相乘再去 average， 那个值还是会掉下来。那就是为什么在我们这一个 case。Okay, you can imagine in the case of triples, when two triples are partially separated and partially overlapped, although if you look at the envelope, they are partially overlapped, but you need to care about the local fringes of the overlapped parts. Okay, so for a triples, like an up triples, the fringe density increases. So this is blue part, this is red part. When the second pulse partially overlap, main peak here, 你是用第二个 pulse 的 blue part 跟第一个 pulse 的 red part 去 overlap. Local fringe densities are very different, and their product complex overlap integral could be very small. Okay, so that's why even though their envelopes still overlap, but the autocorrelation value could be very small. Can justify why transform limited poles and triples give rise to the same